This is the story of one of the most remarkable developments of our time. The story of man's new ability to purify wastewaters and reuse them for any normal purpose. Yes, even for drinking water, if the need and the desire exist. Americans are becoming increasingly concerned about their nation's water supplies. In more and more places, there simply isn't enough water to meet all the beneficial uses which people wish to make of it. In some places, the degree of purity of the water is not at issue. But in others, upstream contamination inhibits the uses which may be made of the water downstream. Any development which helps people to upgrade their water supplies means that each drop of water is multiplied in its usefulness to man.
One of the greatest challenges facing our society today is that of conserving our priceless natural resources in a period of rapid expansion and population growth. The problem is especially acute here in California, where we have tremendous growth and a wealth of scenic beauty. One aspect of the problem, the threat of water pollution, is being met head-on at Lake Tahoe, in California's spectacular High Sierra country. Along the lake's popular and fast-developing South Shore, for example, ultra-modern sewage treatment facilities are now eliminating all causes of pollution. Such plants remove the nutrients from effluents which stimulate algae growth and cause the premature aging of lakes. Local agencies in the Tahoe area have committed themselves to agreements which provide that no more sewage and solid waste refuse will be allowed to enter the surface waters of the lake basin, and that all such wastes will be exported from the watershed by the early 1970s. I consider this to be an outstanding example of how to provide for both today's use and enjoyment of the lake and to ensure that it remains an unimpaired natural resource to be enjoyed by our children and their children's children. The Tahoe solution could, and I'm sure will be, applied to many pollution problems. The technology now being employed at Lake Tahoe could well become an important new weapon in the fight to clean up America's waters.
Lake Tahoe, more than a mile high in the Sierras on the California-Nevada border, is considered to be one of the 3 clearest lakes in the world. Even today, an 8-inch white disk is visible at a depth of 130 feet. This compares favorably with tests made nearly 100 years ago, proving that Lake Tahoe is not now and never has been polluted. But Lake Tahoe is coming under increasingly heavy pressure from people with summer homes there, from people who flock to casinos on the south and east shores, from tourists who come to see it, to go boating upon it, to swim in it. The potential for pollution exists, and as Governor Reagan has pointed out, steps are being taken to prevent it. In nature, lakes die through a process called eutrophication, when nutrient materials like phosphates and nitrates are present in the water. Algae feed upon them, and in time give rise to the growth of water plants. Eventually, the plants die and decompose, providing a base for the growth of more plants, and the mass of peat materials spreads out from the shoreline, building a flat, solid bed which often makes excellent farmland. Lake Tahoe, being very deep and very pure, has largely escaped this process. But if man-caused nutrients were to enter the lake in quantity, the process of eutrophication would be vastly speeded up, and the early death of the lake might be foretold. Our story really starts at the South Tahoe Water Reclamation Plant. Here, a far-sighted board of directors, working with U.S. government agencies, engineers, and industry, has developed a 7-stage wastewater treatment plant whose end product is reclaimed water so pure that it may be drunk without any harmful effects whatever. The primary and secondary stages of the plant are conventional and are similar to those found in cities and sanitary districts throughout the civilized world. The tertiary or third stage, however, is the most advanced of its type in existence. It embodies many engineering achievements and holds out the promise that wastewaters can be reclaimed for beneficial uses almost anywhere. The tertiary process starts with the chemical clarification of the secondary effluent. At the entrance to the chemical clarifier, lime is introduced into the effluent in a flash mixer. This serves two purposes. It makes the water more alkaline, an important step in the later removal of ammonia, and it helps to form calcium phosphate, thereby removing the phosphate, one of the nutrients causing algae growth. The light-colored, cloudy material in the chemical clarifier contains calcium phosphate, most of which settles to the bottom by gravity and is removed by sweeper arms. The next step is the stripping of ammonia from the effluent. Ammonia, which is an important constituent of domestic wastes, contains nitrogen, another source of nutrients upon which algae flourish. The ammonia stripping tower is a series of hemlock slats through which the water drips from the top to the bottom of the tower. A powerful fan draws air through the slats at the rate of 700,000 cubic feet per minute and blows it out the top of the tower. As each drop of water strikes a slat, it breaks up into mist-like droplets, and the rapidly moving air pulls the gaseous ammonia right out of the effluent without any noticeable odor added to the surrounding air. The next step is the physical filtering of solids from the effluent. There are 6 large pressure filters which operate in pairs. Each filter is packed with materials or media of different sizes and specific gravities. The media are placed so that the largest and lightest particles are at the inlet, and the smallest and heaviest particles are at the outlet. The result is that the solid waste can be accumulated throughout the entire depth of the filter beds, and a high rate of flow-through can be attained. The filters are backwashed periodically with clean water. The output of the filters is monitored on automatic controls, which tell the operator by signals if any changes in chemical additives or operating procedure are required. Now comes the final step in tertiary treatment, removal of dissolved organic materials by adsorption in columns filled with granular activated carbon. The granular carbon in these 8 columns is capable of removing dissolved organics, even DDT, which are still present in the water, causing unpleasant odors and a yellowish color. The water passes from the bottom of each column to the top, while fresh carbon is added at the top and spent carbon withdrawn from the bottom. Each column contains about 22 tons of granular activated carbon, equivalent to more than 4 million acres of surface area. It would be extremely expensive if unused carbon had to be added to keep the columns at top efficiency. But at the Tahoe plant, the carbon is thermally reactivated in a multiple hearth furnace at temperatures up to 1,700 degrees using natural gas. The impurities are burned off, and the reactivated carbon is returned to storage for reuse. About 95% of the granular carbon is recovered for reuse in this reactivation step. In a somewhat similar way, a large percentage of the lime employed in the plant also is recovered for reuse. Most of the sludge removed from the chemical clarifier and from the recarbonation basin under the ammonia stripping tower is piped to the top of a building in which 2 multiple hearth furnaces are housed. Here, on the top floor, are large centrifuges which are used to dewater the spent lime slurry. The lime centrifuge also serves another purpose. It helps to separate the spent lime from the lighter phosphates with which it is associated. The lime is recalcined in a multiple hearth furnace heated with natural gas. Carbon dioxide from the stacked gases of the furnace is introduced into the effluent as it leaves the ammonia stripping tower, adding the materials necessary to capture calcium ions and change them to calcium carbonate, which can be precipitated out of the mixture. After centrifuging, the dewatered spent lime is introduced into the recalcining furnace, where carbon dioxide is driven off by heat at temperatures up to 1850 degrees Fahrenheit, and the remaining material emerges as quicklime or calcium oxide. After cooling in a special disc cooler, it is returned for reuse. Another feature of the plant is the incineration of sludge from the primary and secondary clarifiers. The sludge passes through a centrifuge and multiple hearth furnace similar to the lime recalcining equipment. The flue gases then go through a supercooler and scrubber, which removes all particulate matter and discharges odorless, plumeless gases into the atmosphere when the gases are not recycled in the process. The ash residue is the only waste material that goes into the environment. It is sterile, and the phosphate it contains is in an insoluble form. This is a look at the setup of the complete tertiary plant, producing an effluent which, when chlorinated, is pure enough to drink. There's really no reason from the standpoint of conservation why the effluent from the plant could not be returned to Lake Tahoe. However, state law requires that all wastes from the Lake Tahoe basin be exported outside the basin. Therefore, the effluent from the South Tahoe plant is pumped over a 1,200-foot lift through Luther Pass to a new artificial lake on Indian Creek, which has a capacity of 1 billion gallons of water. This water, the output of the South Tahoe tertiary plant, is so pure that it is perfectly safe for boating and swimming, and already the reservoir is being used for recreational purposes. In addition, the water is turned over to an agricultural irrigation district, which sells it to farmers in the Indian Creek area for watering their crops. What is the significance of the South Tahoe water reclamation plant for the world today? The significance is great. Wastewater can now be reclaimed for a multitude of uses: for processed water for industry, for domestic and agricultural irrigation, for recreation. Not only this, but pollution from domestic waste can be stopped dead in its tracks. Wastewater from all the familiar sources can be reclaimed and returned to our rivers, streams, and lakes, leaving them as clean as if the source of potential pollution did not exist. This means that the surge of building in and around our cities can continue without adding to the pollution factor, and our large rivers and harbors can be clean again, not the noxious cesspools many are today. What does tertiary treatment cost? Experience at South Tahoe indicates that this high degree of tertiary treatment costs approximately the same as primary and secondary treatment combined. Thus, the total cost is roughly doubled. In many cases, part of the cost can be recovered from the reuse of effluent waters. In other cases, tertiary treatment will prevent pollution that has become unacceptable to the citizens of an area. So, the lesson of the South Tahoe water reclamation plant is, man now has the capability of purifying his wastewaters to the point that pollution can be prevented into the foreseeable future. And that's a big answer to a mighty big problem.